This time, I'm going to talk about Heston model simulation in Python. The Heston model is a mathematical framework used to describe the dynamics of financial derivatives, particularly options. The model aims to address some of the limitations of the Black Scholes model, which assumes that volatility is constant over time. In the Heston model, volatility is not constant, but follows a stochastic process, which means it can change over time due to market conditions. This makes the model more flexible and realistic, as it can capture the observed volatility clustering phenomenon seen in financial markets. Let's take a look at the three key components of a Heston model. First, the Heston model starts with the stochastic differential equation that describes the movement of the underlying asset's price. It's similar to the geometric Brownian motion in the Black Scholes model, but incorporates stochastic volatility. Secondly, in the Heston model, volatility is itself a stochastic process. The volatility follows a separate stochastic differential equation. Lastly, the Heston model introduces correlation between the two Wiener processes, W1 and W2. The correlation term ρ captures the interaction between the stock price and its volatility. A positive correlation means that when the stock price goes up, the volatility tends to increase, and vice versa. Now, let's take a look at the three formulas of Heston model. First, it describes the price change of the asset. Second equation describes the volatility change of the asset. And the third equation describes the correlation between W1 and W2, all those two Brownian motions. And as I mentioned before, ρ is a correlation coefficient for W1 and W2. And St is the price of a specific asset at time t. Square root Vt is the volatility of the asset price. And sigma is the volatility of the volatility. So, please note, although the volatility is not constant in Heston model, the volatility of the volatility sigma is constant in Heston model. And R is the risk-free interest rate. Theta is the long-term price variance. So square root theta will be the volatility of the long-term price. And kappa is the rate of reversion to the long-term price variance. Here, the asset is modeled as a stochastic process that depends on volatility Vt, which is a mean reverting stochastic process with a constant volatility or volatility sigma. The two stochastic processes have a correlation ρ. Now, let's compare Heston model and Black Scholes model. You can see the Black Scholes model is not considering volatility dynamics, correlation, volatility of volatility, or mean reversion. But Heston model consider all those 4 factors. The Black Scholes model has a constant drift, but Heston model may include drift and mean reverting term. When we consider the option pricing, Heston model can handle more complex options, but Black Scholes model is limited to simple options. Heston model accounts for volatility clustering, but Black Scholes model assumes constant volatility. When you calibrate all those 2 models, Heston model needs more parameters, so the calibration process is more complicated. But Black Scholes model has fewer parameters to calibrate. Of course, Heston model has more complex mathematical structure, and Black Scholes model is relatively simple and tractable. When we try to simulate Heston model, the first question we will have is how can we generate correlated random normal variables? Let sigma be the covariance matrix between 2 random normal variables. So the correlation will be rho here. And let's say the random variable has a mean mu1 and mu2. So we can write this as a 2-dimensional vector. We can then draw from the following distribution. Wt is a random vector of dimension 2. It represents a pair of correlated random variables. Tilde is read as distributed as or follows the distribution. It indicates that the random vector Wt follows a specific probability distribution. And this n mu sigma denotes the type of the distribution. N refers to the normal distribution, and mu sigma represents the mean vector, this mu, and covariance matrix of the multivariate normal distribution. Now, let's go to Python to see how can we simulate this Heston model process. First, let's generate correlated random variables. We can use multivariate normal function in Python to generate 2 series of correlated random variables. I will upload my Python code to my GitHub, so you can download it and try it by yourself later. Let's run the program. You can see the 2 series of random variables is correlated. When one variable goes down, another variable goes up. and the correlation is negative 0.6767. If you run it again, of course it will give you a different result. You can see every time it will show the different pattern because of the randomness, but in general, those two series of random variables are correlated. After we generated correlated two series of random variables, we can use them to run the simulation for the Heston model. Again, I will up this source code to my GitHub too, and you can download it and change the parameters to check it out by yourself. And here, I will use this function to generate Heston model path. This function is used to calculate call price with Black Scholes model, and this function is used to calculate put price with Black Scholes model. As I mentioned before, because in Black Scholes model the volatility is constant, so by comparing the price between calculated value from Black Scholes model and the calculated value from Heston model, we can calculate implied volatility. When I generate Heston model path, I have several different scenarios. First is we have high positive correlated asset price and asset volatility, and the rho is 0.9. Another scenario is I have high negative correlated asset price and asset volatility, and the rho is negative 0.9. Another one is I don't have any correlation between asset price and asset volatility, so rho is 0. Another one is I just generate some random Brownian motion as a benchmark, and for the simulation I will run 50,000 paths. And lastly, I will see the distribution with a different correlation and draw a graph. Now let's run the program. Because I'm generating 50,000 Heston paths, it will take some time. Now we got our results. You can see the implied volatility smile calculated from Heston model looks like this. And 100 is a spot price. And with a different strike price, it shows different volatility. And for the simulation, you can see we have 10,000 steps, and the stock price starts from here, 100, and then goes like this. And this shows the volatility simulation. You can see, same, we have 10,000 time steps, and the volatility goes like this. And theta, if you still remember, is the long-term price variance. So the square root of theta means volatility. So in the input, we have theta 0.04. So the square root of theta is 0.2. And if we come down for the distribution, if we have positive correlation 0.9, the distribution shows like this. And if we have negative correlation, the distribution looks like this. If we have no correlation at all, means rho equal to 0, you see this distribution shows here. And similarly, if we just draw the Brownian motion, it shows very closely like no correlation, means when rho equal to 0. This is how you can run Heston model simulation in Python. Please provide your comments and subscribe to my YouTube channel. Thank you.